Here's our video notes on Gay-Lussac's law. So Gay-Lussac's law is talking about pressure and temperature. So the pressure of a fixed mass of gas at constant volume varies directly with the Kelvin temperature. So again, temperature needs to be in Kelvin, and then this is a direct proportion, so hopefully you're thinking about that the Charles law was also a direct proportion. So our graph should look something like this, where it's showing as one increases, the other is going to increase. So my equation is P1 T2 equals P2 T1. Please watch your 1s and 2s again, just like in Charles' law. So now if we look at a video kind of diagram of this, much like we did with Charles and Boyle's, we're going to look at the relationship between gas and temperature here. And the movable piston on this one, how it's different, again, is that it's going to be set with pins now. As with Charles and Boyle's law, the volume was able to change. With Gay-Lussac's law, the volume stays constant. So just a reminder, gas pressure is created by the collisions between the moving particles and the walls of the container. The gas pressure is defined as the force of these collisions divided by the area of the walls. Hopefully you're getting relatively comfortable with what we mean by force and collision and how pressure is created, because this is the third time you've seen them in terms of talking about how those particles move. So the number of gas particles is kept constant, again by being sure that the system has no leaks and that the pin here is keeping that piston from moving. So as we look in the example here, so when the temperature is increased, the average velocity of the particles increases, and it increases the average force per collision. It increases the rate of collision. So anytime we increase the temperature on something, our particles here are going to move faster because the kinetic energy is increasing. So because of that, and because those molecules are going to hit the side of the container more, those molecules are going to increase the pressure, especially since we're keeping the volume constant. And so as we look here, we're seeing that the temperature and pressure are both increasing as you see those molecules move faster. So the increased temperature leads to an increased average velocity of the particles, the increased average force per collision, and increased rate of collision. Thus, we increase the total force with constant area, and thus we increase the force per area and the pressure. So that's just talking about as you increase the temperature, the pressure is also going to increase. And the reasoning why that happens is because those molecules are moving faster. So it's always important to try to identify why something is happening and not just say the what. It's always important to know the why. So just to sum up, if the number of gas particles and volume are held constant, the increased temperature leads to an increased gas pressure. A decreased temperature leads to a decreased gas pressure. So there's kind of your diagram of Gay-Lussac's law, and now let's go and practice some of the math. So again, the effects of increasing the temperature of a sample of gas at constant volume, the molecules move faster, so the pressure increases. So here just showing, look, we've got a fixed volume, which is important. With Boyle's and Charles' law, we didn't necessarily have a fixed volume. That could be a variable. So because we're talking about volume, because we're talking about temperature and pressure, we know that volume and number of moles is held constant as we go back and review our 4 measurable qualities of a gas. Let's do a math problem here. A gas in an aerosol can is at a pressure of 3 atmospheres at 25 degrees Celsius. Directions warn the user not to keep the can in a place where the temperature exceeds 52 degrees Celsius. What would the pressure in the can be at 52 degrees Celsius? So you should always be thinking, anytime you see degrees Celsius, you should be thinking, I know I need to change that to Kelvin. So let's write out our variables and make sure we understand what our givens are. So P1 is 3 atmospheres. So just like we did with Charles' law, I really like to write out the variables, especially since our T1 and our T2 are switched in the algebraic equation. It really helps you avoid that mistake. So P1, P2 is our variable. T1, and again, it also lets you show your math for that T1, so 25 degrees Celsius, and then we know we need to convert it to Kelvin, so it would be 298 Kelvin, and then 52 degrees Celsius, or 325 Kelvin. So what I like to do now is write out my algebraic equation. As we get our givens here, I like to write out my algebraic equation. I don't prefer the fraction equation simply because when we get to the combined gas law, it just makes it a little bit more difficult to keep our variables straight. I prefer you do it and set it up like this. So I prefer that you write out your equation here and then write your variables underneath. So in this example, I prefer that you would write the P1 T2, so P1, T2, P2, T1, and that you write your variables underneath. So 3 atmospheres, our T2 is 325, and that equals P2, which is our variable, and T1, which is 298. Okay, so this is how I expect you to show your work for us in class in terms of Gay-Lussac's law. So then when we solve here, we know that pressure is 3.27 atmospheres. So Gay-Lussac's law is very similar to Charles' law, where we've got the T2s are switched, so please make sure that you watch that. Okay, so we just need to know in our algebraic equation that the T2 is on the left side and the T1 is on the right side. So that ends our notes on Gay-Lussac's law, and we'll start up with combined gas law on the next video.